In this video, we consider the application of Metre Bridge, and we consider the application of Metre Bridge in the case of what we call Metre Bridge. Metre Bridge is also known as slide bridge. So this is the Metre Bridge. There is a wooden panel. On that wooden panel, metallic strips are arranged. These are metallic strips, thick metallic strips, so that the resistance will be minimum. And between the points A and C, there will be a uniform cross-section wire connected. Appreciably high resistance will be there. Sometimes you might have a gap, constant gap. Okay. Standard resistance wire. That's of uniform cross-section, so that its resistance per length must remain constant. And on that we make the connections to find the resistance of a given wire. For that, there will be a resistance box connected in the first gap. This is a gap. In that first gap, a resistance box is connected. Second gap, we connected what? The unknown resistance, or the resistance whose value is to be found. And a galvanometer is connected to the midpoint, and the other end of the galvanometer is connected to a jockey, a probe that can be slide over the length of the wire. Okay, so when you slide that jockey over the length of this meter wire, this is exactly of 1 meter. Don't press that jockey too hard on it, so that the area of cross-section of the wire changes. Don't do that pressing. Slightly move it on that. Okay. Then there is a supply connected here, and a key is introduced so that to save the supply power. Whenever it is needed only, you put the key and start. Now, how to find this unknown resistance using this one? For that, we introduce the key over here so that the current starts flowing through this. One part through this way, another part through this way, and some of them will be flowing through the galvanometer also. And after that, we place the jockey at this point close to A, so that the galvanometer shows deflection on one side. And next, you press the jockey at this point so that the galvanometer shows the deflection on the opposite side. So the galvanometer will be having a scale like this, that the midpoint is 0 and the needle stays here. Left deflection, right deflection. Depending upon the direction of flow of current, you will be getting the left or right deflection. So, by pressing the jockey at this point and at this point, you are getting the deflection on either side, means somewhere along the length of the wire, you will be getting a 0 reading. Okay? Once you get the 0 reading in the galvanometer, that means that at that point, the bridge is balanced. Okay? So, to begin that process, you check the correctness of the circuit and all that. Now I introduce a resistance R in this box, and I start moving the jockey from A to C slowly. A to C. Then, as I move from A to C, the deflection in the galvanometer starts moving from left to right, and as the jockey reaches at this particular point, the galvanometer is found to read 0. That means that at this particular point, the galvanometer reads 0 means there is a length of the wire coming. That length of the wire is called balancing length. So at this length of the wire, the voltage is now balanced. So the remaining part of the wire length will be 100 minus L centimeter. So here it is centimeter. This will be exactly 100 minus L centimeter, because the length of the wire is 1 meter, and that is why the name meter bridge. Okay. Now at this particular point, as the galvanometer reads 0, no current is flowing through this way. That means the current reaching here will be flowing through this part, and the remaining flows through this part. Now let me take the points A, let this be B, C and G. Point A, B, C and G. Let's see. Between points A and B, the resistance R is coming. So, resistance R. Between points B and C, what is coming here? X. Between point C and J, there comes a resistance. That resistance is the resistance of this length of the wire. That means rho into 100 minus L by E. You know the equation? Like that, between points J and A, rho into L by A, where A is the area of cross section of this wire, rho the resistivity of the wire. We studied. Between points B and J, who comes to this galvanometer. And between points A and C, the supply is coming. Now you see, this V-stone spread in the balanced state, you can have a V-stone spreads connection. That means that the balanced meter bridge is exactly what you say, a V-stone bridge. So what is the principle of working of meter bridge? If anyone asks, you can very well say it works on the principle of V-stone spreads in the balanced state. V-stone spreads in the balanced state. Okay. Now you know the relation there, already studied. Take that directly into this one. You get R by X is equal to rho into L by A divided by rho into 100 minus L divided by A. That corresponds to R by X is equal to L by 100 minus L. L by 100 minus L. Therefore, the unknown resistance X will be equal to R into 100 minus L divided by 10. X is equal to R into 100 minus L divided by L. So this formula you can use for finding the resistance X from this. times you will be putting the resistance box here and unknown resistance here. Then according to the final result, that balancing condition also will be shifted. Okay. So this is one thing to be remembered. Alright. Now, suppose that the deflection, if anyone asks why when you put the jockey here, why the deflection goes on one side and press the jockey here, deflection on the other side, you can get it from the flow of current. Okay? When close to this, the potential drop across this one will be very small, here it will be very large. So accordingly the galvanometer current flows in that particular manner, that it will be flowing in this way. But when it comes here, flows like this, and therefore galvanometer shows deflection on one side and at this to the other side. That is based on the flow of current through the galvanometer. Now, another question possible here is, what happens if we connect a high resistance in the path of the galvanometer? That means, when I connect a high resistance here, high resistance, what will happen to the balancing condition? From this equation, if you understood properly, the balancing condition not changes, because once the bridge is balanced, the current flowing through the galvanometer is zero. We are taking the reading corresponding to that. When the current flowing through this path is zero, whether you connect a high resistance here or not, it's not making any difference. Understood? That is one important question possible in YY relating to meter bridge. Okay? So, this can be a 3-mark question. Draw the diagram of a meter bridge to find the unknown resistance. Okay? That's all.